Okay, good day, everybody. Critical transitions in complex system seminar series is being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research in Germany. This is our fifth season, first talk of the fifth season. So that's very impressive. We started in 2021. This webinar series brings together experts from diverse fields such as climate science, fluid mechanics, neuroscience, ecology, etc., and aims to disseminate the state of the art in prediction of critical transitions in these diverse fields of study. The seminar takes place every month on the last Monday of the month. So please mark your calendars. Before I introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones and kindly use the Q&A box in Zoom to ask the speaker your questions. Just type your questions there, and at the end, the speaker will address them one by one. And with that, let me introduce today's speaker. Dr. Frank Hellmann studied physics at Munich, Edinburgh, and Marseille. He obtained a PhD in quantum gravity from the University of Nottingham. In 2014, he switched fields to join Jürgen Kurz at the Complexity Science Department at PIC, Potsdam Institute for Climate Impact Research. Since 2018, he has been leading the group on infrastructure and complex networks there. Today, Frank will speak about dynamics of modern power grids, a complex system perspective. Welcome, Frank. The floor is all yours.
Thank you. Can you hear me?
Yes, excellent.
Very good. Thank you very much for the invitation to present our research here at this by now famous seminar. I'm going to speak about the dynamics of modern power grids and specifically how we have done a lot of research on them using a complex systems perspective of the system and a set of tools that are not directly taken from but inspired by complex systems research. Now, this work I will present today is collaboration with my students, Anna Büttner, Hans-Würfel, Jakob Niehaus, and Nina Kastendiek, who are currently my students, and collaborators Johannes Schiffer, Robin Delabay, and more. Without further ado, let me talk a little bit about the power grid as a complex systems and what that entails from my perspective. You can certainly understand and believe that the power grid is a critical system to modern societies. It's becoming more so as we electrify more and more of our energy usage. It's also a highly dynamical system in the sense that emergent, complex synchronization processes play a foundational role in the power grid. This power grid is undergoing a rapid change, and this rapid change, of course, is originally driven by the need to address climate change, the need to decarbonize the entire economy and our electricity system in particular. However, by now, it's no longer just sort of policies driven by climate change ambition that lead to changes in the power grid. The economic reality of power grids has fundamentally changed in the last few years. The price of solar has plummeted and continues to plummet. And we are now in a situation where solar is essentially almost, you can consider it free if you have the land and the labor to install it. The solar cells themselves are relatively free, at least in large parts of the world. And you can see how that fundamentally reshapes our whole thinking about the power grid. It's no longer a question what is the most efficient, cheapest way to provide a system of energy for the entire need of the population it serves. It's now the question, what is the best complementary technology to go with solar? And we're seeing this rapid change in California, where just in the last few years, we've seen a massive, massive installation of batteries. This is California, is like depending on how you count, the fourth or fifth or sixth largest economic region in the world. And it now in the evening hours, this is just a random day, this is from yesterday. In the evening hours, you have 25% of electricity provided by batteries. So we are already in a situation where new actors are coming into the system at massive speed And this is driven by economics. This is no longer driven by policy, it's driven by economics. So this will presumably sooner or later reshape energy grids everywhere. Like I already mentioned, the grid relies on continental scale emergent synchrony. Without synchronous motion of all the generators, of all the turbines that provide energy in the classical grid, there can be no stable power flow. If the synchrony is perturbed, for example, if a cascading failure splits the grid, an overload of one line leads to an overload of another, and the system breaks apart into two parts, both parts need to re-establish synchrony within themselves, or you get a massive scale, continental scale blackout. This happened in Spain, in the Iberian Peninsula, even though it wasn't exactly so straightforward, and we still don't really know what exactly happened earlier this year when there was a blackout there. But we saw there that the entire system collapsed essentially in a matter of seconds. So we're looking at extremely fast timescales, and we're looking at an emergent synchronization and organization that keeps the grid stable. There is no central agency that gives a beat by which the system swings. This has to be established dynamically. Now, this has come into focus in recent years. There's now in Germany a roadmap specifically focusing on this aspect of system stability, because it was understood that system splits that have occurred in the past would not be stable, would not lead to three stable regions that can then be reconnected under the planning that we already of systems that we're already doing right now. So the final system that was part of the 2021 sort of decadal plan would not be stable as it is written in the original plan. So let's go a little bit to make it a little bit more tangible what the challenge actually consists of. We are replacing giant turbines, like the one on the left, with programmable inverters that control how batteries, how solar cells, how other sources of flexibility interact with the grid. And this means we're not just swapping out one technology for another. We're replacing a problem of coordination among 10,000 or so well understood machines that are heavily monitored with a system of millions of machines in a much larger, from a topological perspective, much larger network, and with dynamics that are not understood. So I think you can see and might agree that this is a setting in which network science, complex system science, and a more general approach than trying to make a detailed model of every aspect of the system and simulate it and monitor it and tightly control it are really called for. This is the central challenge now for the final phase of the energy transition, to achieve this dynamic stability of the system at these short time scales, a few seconds, using these millions of distributed devices. So how do we actually do this? Or what is our perspective on how we might go about understanding or meeting this challenge? So this is essentially, we say, back to first principles and back to physics, because we have no way of actually getting engineering style detailed models of each individual device. We have no way of getting detailed information of the state of the system. So let's go back to first principles and physics and see where we can go from there. And this will be sort of the part one of my talk, which is going to focus on the modeling aspect and how we identify the dynamical behavior of systems that are themselves unknown in this context. Now, one more technical detail about the power grid, especially at everything that is not super local. Power grids generally have at least three phases. So you have every voltage, every current comes in three copies. And these three phases are balanced so that the sum of the voltages is always equal to 0. Then you have some sort of sinusoidal oscillation hopefully kind of sinusoidal, might be varying by a bit. And you can use a simple linear coordinate transformation from these three-dimensional phase space, which is really a two-dimensional phase space due to the balance condition, to the complex plane in such a way that you get an approximate complex oscillator that is oscillating in the complex plane. And then you can take, for example, the algorithm of that, unroll the phase, and then you see that the fairly complex and jittery motion in the top of the three phase voltages gets translated into a fairly straight line in the bottom right corner. And what you can also see in the bottom right corner in the phase description is that the motion in the top is speeding up. So maybe you noticed that before, maybe you didn't, but it's certainly much easier to see this type of dynamical behavior, like a slight speed up in the rotational speed in the phase description than in the original three-phase, as in the original voltages. So this is this is the physics and some nice coordinates for these physics. And knowing about these physics, we started thinking about the question, how would we describe this from a complex oscillator perspective or from an oscillator perspective? And of course, a standard method in complex system science is to introduce and work with phase variables. So phase variables plus phase orthogonal amplitude variables allow us to universally describe weak interactions between oscillators using phase response functions. And I'm not going to go into recall all this into detail, but essentially use this isochrones in order to see what is the impact of the weak coupling on my oscillator. And then you can describe how the oscillator varies, and the coupling is entirely given as a function of the phases, and so on. Now, this doesn't directly map to our use case in power grids. Why not? Most importantly, because we don't have weak coupling. We have strong coupling. We have extremely strong coupling. We are transporting massive amounts of energy. And we don't have oscillators that just sort of do their thing and then sometimes are a little bit perturbed by coupling. The oscillators exist exactly in order to maintain a certain state in the coupling. On the other hand, we don't need to mathematically derive phase variables either, because we have already at least approximately phase variables just by coordinate transformation, because the system is designed to be close to a limit cycle. So now this led us to the fundamental idea, the foundational idea of the research we've done in recent years, which is we want to keep the full physics of the coupling, describe it in terms of invariance of the approximate limit cycle phase. So for example, amplitude and phase differences. Then we assume also a phase shift invariance of the nodal dynamics, which allows us to reduce the complexity of nodal dynamics. And we can write an invariant response. We write the nodal dynamics as an invariant response to the state of coupling. In some sense, this turns the phase response picture upside down. We're no longer just reducing, we're starting with variables that don't maintain the exact limit cycle, like the phase variable is defined in terms of the limit cycle of the unperturbed oscillator, but we're starting with variables that are well suited to describing the precise state of the coupling. And then we are approximating the nodal dynamics instead of approximating the impact of the coupling on the node. We're approximating the impact of the node on the coupling, if you want. How does that look in practice? So I'll give you a few equations. The papers are on the bottom left, where we introduce this way of looking at the system. Like I said, we have a complex oscillator V. We have a phase theta that will often be more natural to use rather than the complex oscillator. The current is just given by something like Ohm's law. Even though this is now all complex numbers, you still get something like Ohm's law here. So the current is just a difference of the voltages. And the state of the coupling is characterized by power flows, which turn out to just be given by this complex number, the voltage times at the node times or at the end of an edge, times the current that is flowing into the in that edge. The complex conjugate of the current, I should say. Now it turns out that the real part of this is really the power, the actual physical power that is transported by the power grid, and the imaginary part has a meaning too. It's the so-called reactive power, which at least when integrated over a whole period can be interpreted as the amount of energy that is currently stored in the lines due to the oscillations and the magnetic fields around the line. Now, like I said, we assume that there's the appropriate symmetry in the node response, which means that with theta being the complex phase here, the dynamics at the node do not depend on the imaginary part of theta. And now there is an additional assumption which we make, which is that the system is somewhat close to a desired state of coupling, and this desired state of coupling is just given by the complex power. And the real part of theta corresponds to the amplitude, so that's the voltage magnitude. That's usually within 10% of specified bounds. So we know this is small. This delta real part of theta here is actually small. And we get a nice set of equations where the nodal response is characterized by two matrices. Our hypothesis is that these two matrices can parameterize the dynamical behavior of a large swath of dynamical actors that participate in the power grid and that are part of the synchronization procedure in power grids. So you have some detailed complex models with a lot of internal control loops, a lot of electronics, a lot of nonlinear things. And our idea is we want to map all this to these two matrices. Is that possible? So to test this, we worked together with the TU Dortmund and with BTU Cottbus, with colleagues there who did experiments and sophisticated simulations for us. And we found out that actually, yes, this works. And this is now published since a few months in IEEE Transactions. So also convincing enough to the engineering community. And this is, we have a fantastically good fit as long as we are in distribution, but even out of distribution. So meaning we identified the individual oscillators, the individual devices, and then put them in a new scenario where they were heavily perturbed, where there was a sudden disconnection of the system from the main grid. We still could capture the dynamics very, very well. So I'm very happy with this sort of breakthrough result. Let me give it briefly another perspective. I sort of motivated this now from a phase reduction perspective, but there's another way to look at it. And this other way to look at it is something that we also only understood relatively recently how it exactly comes about, which is this symmetry assumption, which is somehow a very natural assumption, actually has a correspondence in the engineering world. In the engineering world, it is typical to go into what they call a co-rotating frame, and then to assume that the dynamics remain independent of time. So you introduce some rotation and a time-dependent coordinate transformation, and then the system remaining independent of time despite a time-dependent coordinate transformation means it has to have a symmetry. And this symmetry or this assumption of time independence that is made all the time in the engineering world can be translated to a U1 symmetry. And if you have a U1 symmetry, well, then the fact that something like a normal form of a Hopf bifurcation or a Stewart-Landau oscillator might show up is completely natural, of course. And the equations I showed you before are very much generalized Stewart-Landau equations. And they can be very easily read this way, where you have some, dynamics of the phase, the complex phase, or dynamics of the complex oscillator. And then you have this multiplied by some invariance. And in our case, also the coupling is invariant. And this is not so typically studied in Stewart-Landau. But in our case, it turns out that this is the most natural way to get, or this is a very natural thing to write down for power grid dynamics. So to summarize this first part, power grid dynamics are well described by a class of generalized Stewart-Landau oscillators They're parameterized by two matrices, or equivalently a linear time invariant system. And this provides us with a bridge between power system research and complex system science. We can now empirically validate our results. We can look more systematically if I make more complex assumptions, if my parameters are more further from sort of some standard set of parameters, how does the collective behavior change, etc. And all of this is, I would say, is just beginning. Yeah? We haven't really done all this, but it's just now become possible. And the other thing that is now possible, due to having a unified mathematical form of the equation, we can even pursue analytic results. And this will be the second part of my talk now. Having sort of put up a model and claimed, and you need to read and believe the papers to see that this model can actually describe power grid dynamics as they occur in the lab, at least. How do we analyze these? Now, if you want to understand the stability of a networked system, there's standard methods available, of course, from the complex system side. And I think most standard method by far is a master stability, where you assume that your dynamic has a certain factorizing form. Due to this factorizing form, your eigenvalues, your eigenvectors have a factorizing form, and you can come up with this formula for your eigenvectors. You can come up with this master stability function. Now, our setting is more heterogeneous than this in multiple ways. So first of all, we have different Jacobians at different nodes. This in itself might not be completely kill the application of master stability. The number of dimensions per node can also vary. We have more complex and simpler nodes. Again, you might still be able to get around these problems in some ways. However, the killer problem here is that our coupling is not one-dimensional. Our coupling does not factorize. So what that means is that on the left here, you wouldn't have just one L tensor J2, you would have several L, L1, L2, L3, tensor J2, J3, J4. And that means you can no longer go into the eigenbasis of the coupling, and the coupling starts playing a much more complex role than before. So we need a different way to go about decomposing and analyzing the dynamics. And what I would like to I would like to phrase sort of the results that we have in this direction now in terms of just elementary statements about diffusion dynamics, because a lot of this can be seen as a vast generalization of diffusion dynamics when looked at in the right way. So diffusion dynamics here, we're just doing x dot equal minus Lx. L is a Laplacian. The Laplacian can be written in this way, where the big O plus refers to a block diagonal, or in this case, just diagonal matrix, which has the Ke on the diagonal, and Bs is the signed incidence matrix. So this is a way to write the Laplacian. Signed incidence matrix times edge weights times transpose of the signed incidence matrix gives you the Laplacian operator. Now, it's immediate to see here that if the values that are taken on by set Lz, that this set of values is equivalent to this set of values, where you let y range over the image of Bs, and that this range of values is contained in this range of values. So the range of values of the diagonal operator. And this allows you to say that the Laplacian is positive definite if the edge weights are positive definite. Classic result. Classic result, if the edge weights are positive definite, the Laplacian is positive definite. It's not semi-positive definite always in this case. This is not a necessary condition. There are cases where you can make some of the weights slightly negative and you still get positive definiteness of the Laplacian. So this is really a contains here and not an exact equality, but this is maybe the most important and fundamental result for networked stability. Can we generalize this? Like I said, we need higher dimensional edges, and we potentially need a lot more heterogeneity as well. And we'll get to the further types of heterogeneity, but let us first generalize this to higher dimensional edges. So I'm going to introduce here a generalized incidence operator for each edge. This just selects from the vector x all the states that are neighboring the edge E. And then I get B by stacking all these on top of each other. Now I can still write my Laplacian in this form. The HE now, however, are matrix valued, and the ordinary signed Laplacian, the ordinary Laplacian with signed incidence matrices is recovered if I choose this particular form of the matrix HE, and if every edge has only two neighbors. Then I recover this, and the condition that KE is positive is mirrored in the condition that HE is semi-positive definite. However, the condition that HE is semi-positive definite now also works if I have many more states that are associated to a particular edge. So this is already a significant generalization of the classical result. Now, can we go even further? And for this, it's, like I said, we need to consider the fact that the Jacobians and possibly the dimensionality at each node are also different. So looking at this, we can look at this system where we have the nodal interactions, or the nodal action, and the edgewise interaction. And we can see here that this has somehow the shape of a feedback interconnection. So we have a local dynamic, and we have a feedback given by the interaction on the network that is put back into the local dynamics. Now, the stability of linear feedback connections is well studied in control theory, and I'm going to take you on a small tour of control theory results now to show you where we end up and how they are useful. So in control theory, a differential equation like this, a linear differential equation with some input u, is typically written in terms of a transfer function. So you go to a Laplace domain, you put all the s and a and everything with x on the one side, divide by this, and this gives you a transfer function. If you have a higher dimensional system, it gives you a transfer matrix that depends on the Laplace parameter s, and that transforms your input signal u into an output signal x. If you interconnect two systems, you can calculate that the matrix of the interconnected system is given by this. So there's an inverse of 1 plus h times g, and that is multiplied on the left by g. Using contour integration in the complex plane, plus a few more ingredients, you can show that a sufficient condition for the stability of this interconnected system, given that the individual system G is already stable, I should add, is that the eigenvalues of this system don't cross the negative real axis. And this condition, in turn, gives rise to the foundational equations of robust control theory, like the small gain condition, which says that if G, as an operator acting now in this Laplace space, and H both satisfy a small gain condition, then the whole 1 plus GH can never cross the negative real axis, and therefore the interconnected system is stable. This is the small gain condition. Now, the small gain condition doesn't apply in our case, unfortunately, because one of our systems is 1 over s. It's just an integrator, so this becomes arbitrarily large. However, in 2020, there was a breakthrough result in linear algebra, which was that for the first time, somebody gave concretely the people down here, gave a definition of the phase of a matrix, the phase of a complex matrix that is suitable for feedback stability analysis. How does this work? So we start again with this set of values that is taken on by set C set. And then this is a convex region in the complex plane. If the zero is not contained in this region, the matrix is called sectorial, and we can get a maximum and minimum angle of this region. Now, without going into much more detail, these angles give us a lot more information than simply than we had before about our system. They satisfy in a rather straightforward way two very nice properties for our use case. One is that the sort of conjugating them with a matrix like this can only reduce the range of the numerical values. The second is that here we can trade off the direct sum for a maximum outside, so we can analyze this component by component. And the final one, and this is the non-trivial new result, of course, is that that the eigenvalues of the product of two matrices is bounded. The argument of the eigenvalues is bounded by the sum of the phases of the individual matrices. This is a fantastic result that, for example, in this case that we had before, where we have x is sort of just a derivative of y, and y is this h-wise operator, we recover the condition that the maximum of the phase of the individual HE has to be smaller than pi over 2. However, this now is again a massive generalization of the previous result, because now HE can start to depend on S as well. We can get trade-offs between the left and the right, between the phases here and here, and so on. And what my student Nina Kastendieck and Jakob Niehues did, and in collaboration with several other people, was to work all this out in great detail, actually apply it to adaptive network systems, like here the adaptive Kuramoto model, and we get sufficient condition for stability, which is just that the fixed point has to satisfy this phase bound pi. And in this case, this is actually exactly the same as an independently known necessary condition. So something interesting happens here in adaptive networks. Whereas before, this positivity condition of the Laplacian was sufficient but not actually necessary, it turns out that in the adaptive setting, sufficient and necessary conditions actually coincide, and our phase conditions can access the sufficient and necessary conditions. There are several other test systems that are treated in this paper, but now I would like to go back to our power grids with this. I told you our nodal response is parameterized by these two matrices here. That allows us to write this, of course, as a matrix transfer function that goes from complex power to complex phase variables. And the response of the network can also be written in terms of a single operator here. This matrix only depends on the power flow and on the network coupling. So this is exactly the type of situation we want. We can get the phases, we can calculate the phases of these things here, apply all the machinery of the phase stability, and then get limits on the local dynamics that ensure that the entire interconnected system is, at the end of the day, stable. And this was, of course, a very, very exciting result when we saw that this type of result was possible, when we understood that the phase theorems would enable us to do this, except it doesn't work because both of these operators don't satisfy the necessary conditions to apply phase-based stability analysis. So then you have to do another year or so of work in order to understand how you can tweak and modify both sides in such a way, while maintaining the overall interconnected dynamics, that they satisfy all the necessary conditions. And if you do that, then finally you get to a very, very, very nice stability result that is locally, node by node, tells you how your nodes of your power grid need to behave given the local neighborhood of edges, in order for the entire interconnected system to be guaranteed stable. And we see that some of the conditions, like we tested this in some settings, in some simulations, and then top right, you see that they are sometimes a little bit conservative, but other aspects are actually almost perfectly exact, which is, again, amazing and wasn't really expected, I have to say. I thought we would be getting a lot more conservative results of this method. And this was actually just published by IEEE Transactions on Power Systems last Friday. So this is fresh off the press here. Finally, So one last point. Can we identify topological structures that have an impact on nonlinear stability? So we have now a system a system of equations that gives us the dynamics. We have linear stability covered at least to some degree by analytic results. There are assumptions there, so it's not complete, but we hope to get there. But what about nonlinear stability? Things like Bayesian stability, survivability, all these things. Can we identify which topological structures actually have an impact on these nonlinear measures? And there is a paper we have on the archive that we've been revising for a while now that gives a huge warning sign here. And this huge warning sign is that what we've always done to study this question is to create a large data set of power grid-like topologies and then look at network measures and see whether network measures and Bayesian stability or some other stability measure are correlated, and then say, look, we have a correlation between degree or between being a dead end and so on, and Bayesian stability. And what we found here, to our surprise, was that sometimes when you switch the ensemble, the correlations can vary dramatically. So this system here with 120 nodes was created using our own algorithm for synthetic grids. The Texas system was with another synthetic algorithm that's also highly respected in the literature. And if you look at the maximum neighbor degree, you see that the maximum neighbor degree correlation to Bayesian stability jumps from plus 0.5 to minus 0.2. So we have a dramatic variation here. This shows that somehow you cannot trust these correlations. Correlations are not causation, obviously, but you have to systematically vary the nodal ensembles. And even then we see that there's nothing that is super good at actually predicting our nonlinear stability. So we're further, we would need to incorporate all this nodal dynamical parameters now, and it's unclear how to combine these nodal dynamical parameters properly in these type of centrality measures, for example. You can do this rather more easily in GNNs. GNNs do better in these type of tasks. They do better when generalizing, for example, from the 20 or 100 node ensemble to the Texas ensemble. However, then we have another challenge. How do we extract insights from GNN parameters? So this is, I think, a rather large open questions slide here, and also a little bit of a warning, I guess. Let me finish with some open questions. So generalized Stewart-Landau oscillators can model power grids rather well. We don't know what the limits of these models are. We don't know how to identify these models in situ, so from actual data in power grids. We need to figure out which additional nonlinearities we need to add to improve them. And we know that sometimes the symmetry assumptions are not good in power grids, and we need to go beyond those. We've seen analytic results are possible, at least in the linear regime. So can we remove the remaining unrealistic assumptions? And can we obtain results that are given directly in terms of the in situ data? That would be very, very nice. And I think it's in reach. Nonlinear stability can be predicted using GNNs, and we have a rather large research project going on right now that tries to push this forward and figure out how to use these GNNs to actually explain what topological aspects are important for power grid stability. But this is still very much in progress, also because we are actually working with pretty sophisticated engineering style models in this context and not with our much more manageable Stewart-Landau oscillators. And then I have some open questions that go beyond the power grid context. So we've sort of done something that's complementary to the standard phase approach. We preserve the exact physics of the coupling rather than working from the physics of the limit cycle. And I wonder whether there are other applications for this perspective and this approach. One of the central ingredients is that we know that there's a certain desired state that the system tries to maintain. And a question is, would this be interesting in biological systems, for example, where which have evolved to fulfill certain functions? And then we have this new approach to linear stability in interconnected systems, which I could only very vaguely give a sketch of today. But of course, I think it's also very interesting to explore this and see whether there are other interesting applications for this in adaptive dynamical networks, but also in other types of networked or interconnected systems. We've already looked briefly in one of the papers at settings like ecosystem stability. And again, there's also a question here of extracting topological motifs that are actually relevant, because the way that the method works right now is, again, it's somehow very much like the Laplacian, where it doesn't matter how you interconnect the system, as long as it's connected and the edge weights are positive, the connectivity structure itself doesn't matter. And we have the same structure here. As long as everything is connected, the exact connectivity doesn't matter. But we know that connectivity does matter. So can we reintroduce connectivity in this setting? That's an open question for the moment that we hope to address in the future. And with that, I would like to thank you and open the floor to questions.
Yeah. Thank you, Frank, for this wonderful talk. A really great talk. And I now request the audience to type your questions into the Q&A box. And of course, the panelists can ask the questions orally. Yeah. Already there is a question. Can you see the Q&A box yourself, Frank?
Yeah. You mentioned that the original two matrices in your oscillator model do not meet the conditions to apply the matrix phase results. What are the conditions, please? Excellent question. Let me go back to maybe okay, so one of the challenges that we have with this is on the nodal side, it's very easy to see that there's an issue here, which is this doesn't depend on the imaginary part of the phase. And that means a part of this GNS here goes to infinity as S goes to 0, which is in itself not an issue. And as a matter of fact, the phase conditions are exactly capable of dealing with this. But because other parts of GN do not go to infinity, and in fact, it's only a rank 1 operator that goes to infinity, this becomes an issue. Now, over here, we have a much simpler problem, which is that the range of values actually crosses over to 0. So the phases are actually not defined. It only just crosses over to 0. So it doesn't completely make it impossible to do something. But the problem is that the usual fix for this, which would be to just add a small constant to C, fails exactly because of the symmetry condition on the nodal side. So we have a rather subtle dance between the two sides. And the rank 1 condition, the fact that the thing that we get as S goes to 0 is rank 1, also leads to the fact that this Wertebereich here, this range of values, like overlaps of 0. So it's this sectoriality condition, this condition that everything has to be in one sector, at least for one S, it has to be in one sector, that makes everything tricky.
Okay, thank you.
And I mean, what I can also say is that it's not easy to translate these conditions back into conditions on the J matrices. That's a pretty subtle issue.
Okay, while we wait for the questions, do the panelists have any questions?
Yeah, I have a question, Lakshmanan speaking. So you said that turbine turbines are replaced by millions of programmable inverters with a wide variety of designs and behaviors. So that means you are considering non-identical oscillators, I suppose. But while modeling,
Exactly.
you seem to be assuming all of them are a kind of identical oscillators.
Well, I mean, we show that our parameter setting is rich enough to capture the differences. I mean, we don't assume that we have the same parameters everywhere. And if you have, I mean, of course, if you have a sufficiently rich class of parameters, of course, you can capture everything. It's just a matter of parameter choice. But we are, I mean, let me really to just sort of, we don't make I'm in the wrong window, sorry. So let me go back briefly to this. What we're doing here is we're using the same sort of mathematical form of the equations on very different devices. So one is sort of really grid forming inverters that are built in the lab and interconnected there and measured there. And the other is a simulation setup that is for EMT simulations, so highly detailed simulations about particular controls that are intended to help with this was specifically about inverter limits with respect to current limitation in inverters and how to manage the power laws in these situations. So the power control laws, not power laws in the sense of power laws. So these are very, very different systems, completely different control architectures, completely different things. And we show that the same set of equations can cover both. And so we show that the system relevant aspects of their dynamics is captured well by the universal class that we have.
Okay.
And this is, I mean, what I didn't show here is, but I mean, we do vary, for example, the number of hidden degrees of freedom. So I said this is like a generalized class of Stewart-Landau. So we leave the number of, there's a number of additional scalar variables that we have to allow here in order to really capture this behavior. And we leave that free, and we can do, and somehow it's 1, 2, 3, 4, 5 scalar variables might be necessary to actually capture all the implicit processes that are happening inside the machines. And then we can see empirically how many we need in order to get a good fit to the data that we see. So there's a notion of implicit model reduction here at play here as well. I hope that sort of answers the...
Now, in your slide 14, I think, can you explain the circuit connection 14, I think, 1.4? Yeah. So what is this circuit connection? How does it come about?
The what? Sorry?
How does this circuit, electronic circuit you have shown, device A, device B, how does that come about?
How does it come about? Well, a lot of research groups and companies that are building these type of inverters that have, I mean, these are just supposed to be sort of exemplary, and that like these diagrams are taken from the literature where, and they are exemplary diagrams for these grid forming devices. You shouldn't maybe take them too literally here, even though I believe they are roughly correct. But so you can, these are devices that are built in order to provide a steady voltage source to the grid. And this voltage source has a well-defined frequency, well-defined amplitude, and the frequency and amplitude that it provides are given by some outer control loops. These outer control loops are implementing typically some sort of power droop, current droop, reactive power droop, as well as limiters. I would ask you to not take these words just sort of meant to illustrate complexity. they're not meant to be taken too
I
literally.
was wondering, once you have circuit, then you can write down the circuit equations and then simplify that into an oscillator or something like that.
Yeah, you can do that, absolutely. And we have, as a matter of fact, now with our software that we're developing to actually do equation-based modeling for these power grid devices, we can even somewhat automate this process. So we get this, we can automate this process. You're completely right, and this is sort of what you do here. You first, and we describe this in detail in this first paper. We describe in detail how to go about this, but you start out with sort of these coordinate transformations. So you make your variable choices, your coordinate transformations, and then you can write everything here on the right-hand side as a differential equation. In reality, you need a differential algebraic equation, of course, but we haven't worked out all the details for the differential algebraic equations, but it should be mostly the same.
Okay.
And then once you have everything in these coordinates, and once you've actually made sure that your x coordinates are actually invariant under the phase shift and the limit cycle, then you linearize, and you obtain this. And then you can do something like balanced truncation to model reduce the system, which is something we've tried, but the balanced truncation turns out to be rather worse than going directly from simulation data. So, but this is all very much work in progress. But going directly from equations to these matrices should be, in principle, possible.
Okay. Thank you very much.
Yeah. Now there are lots of questions in the Q&A box.
Can I have one, Sujit?
Oh yeah, go ahead, Prasanthi.
Yeah. So very nice talk. I have one or two questions. One is the state of synchronization that you are considering is it frequency synchronization or phase synchronization?
It's frequency synchronization, so everything needs to have the same frequency, but there are finite phase differences. Otherwise, you would not get a power flow on the system.
Yeah.
And there's a little bit more to it because we also need to keep the amplitude high. So like keep the amplitude at roughly 1. So, but yeah. So we're looking for a synchronized state with same frequency and amplitude roughly 1.
Okay.
That's what we have to stabilize.
Yeah, good. You also mentioned that your analysis is independent of the connectivity, but it involves a Laplacian. So I am wondering how will it become independent of connectivity?
Well, if all the edge weights of the Laplacian are positive, you know that the spectrum of the Laplacian is positive, and you know that the diffusion dynamic is stable. So it's the same statement here. So if you have like we have this vast generalization where you're no longer talking about an edge weight, but now you're talking about the phases of a dynamical system on the edge.
Okay.
But it's the same thing. If the phases of the dynamical system on the edge satisfy the necessary conditions, like some conditions, then this is sufficient to say that the entire system is stable. It's of course not necessary, but it's sufficient to say it's stable. And the question is then, is it very conservative? Is this a very restricted class of systems, or is it actually probing some relevant part of the stable system space?
Mm-hmm. And also, any perturbation that can lead to a cascading failures on the network, can they also be modeled using this?
So yes, I mean, so of course the stability condition is about linear stability, so this doesn't tell you anything about that.
Yeah.
This type of model here that we do, the phase reduction and this normal form or the Stewart-Landau form of the dynamics, that should be well compatible with cascading failure models. So far, I mean, cascading failure models in the engineering literature are often not even dynamic at all. They're just looking at the synchronous state, and then they cut a line and try to find, by root finding methods, a new synchronous state. So these type of simplified dynamics should be well suited to actually going into a cascading model. And it's very easy to augment these with some thresholds. So the thresholds that you have in reality, like amount of current, amount of frequency deviation, or overloading of lines, they're all well captured by this system. So the type of safety limits or security limits where systems shut themselves down and that leads to a cascade. I think this is a model that's actually kind of well suited to that.
Okay.
But we haven't worked extensively on this.
Mhm.
It's not something we've done yet. It's sort
Okay,
of
then.
on the horizon.
Okay, then. Thank you.
So I have a number of questions here.
Yeah, lots of questions.
Do I go from the top or from the bottom? Which is first?
As you wish, you can answer.
The top was first, yeah.
Yeah, top.
As you have mentioned that you are analyzing master stability for the heterogeneous networks, my question is about heterogeneity in connections or dynamics. So maybe this was sort of partly answered here. Let me go here. And I mean, so we are not doing master stability. Like master stability was here as a contrasting point. It's not something that we actually do. Our approach is different. The heterogeneity we introduce is essentially here. You can see it in this equation. This is roughly the level of heterogeneity that we have. There's a little bit more than this, but it's maybe not too important. So you can have a different Jacobian and a different coupling of the network into the local system at every node, and you can have a different dynamic at every edge. So, and interconnection structure, as I already mentioned, actually drops out in our case. So we have a result that's really quite unlike a master stability result because the interconnection structure, again, drops out. But so the amount of heterogeneity that we have here is actually quite significant. So then next question, I'm on a spotty connection, but when you say you were able to capture system dynamics in the linear case, do you mean in the form of explicit analytic dependencies or more general kind of approximation? I'm not entirely sure whether this question now refers to the dynamics or to the stability part. So in the dynamical case, it's like Stewart-Landau. So we're assuming that we are first order in certain nonlinearities. So it's a nonlinear model that actually is required in order to get the full behavior of the power flow equations correct. You need nonlinearities. These are intrinsically nonlinear physics. So it is more general than just linearizing in good coordinates. We're not just linearizing in good coordinates. And the linear stability, yeah, I'm not sure I understand the question about analytic dependencies. I hope this kind of answers the question. As for Port Hamiltonian systems theory, yeah, we've looked extensively at Port Hamiltonian system theory, and it's actually we're working with Volker Mehrmann on trying to connect it, but it's actually proven to be extremely challenging to put everything together in a nice way. Like we're sort of living in different worlds a little bit here. There are certain things you can do. You can sort of do the same you can use the same coordinates in a Port Hamiltonian setting, make a similar assumptions in a Port Hamiltonian setting. But that doesn't seem to buy you very much. Like the Port Hamiltonian doesn't really enrich, like it doesn't seem to talk very well to these assumptions. Like these assumptions are much more natural for the complex oscillator perspective than for the Port Hamiltonian perspective. But it's maybe we're just missing something here. It's something that we keep returning to and we don't have a nice answer yet. In my first part, I presented the LTI formulation as well as the Hopf bifurcation normal form. And he said both are equivalent formulations. Yeah, so this is maybe this was answered by my previous statement. The LTI system, what I presented there, it's not a linear system. We linearize a particular function. We linearize a function of the nonlinearities. So this is like if I go back to the Stewart-Landau, sort of if you put a general expression that is compatible with the U1 symmetry, then you get V modulus V squared, modulus V to the 4, and so on. However, what you typically do is to just truncate this and say, I'm just going to look at everything up to v squared. So I'm looking at the first order nonlinearity. So it's not a linearization in the sense that it leads to a linear dynamical system. That wouldn't work because, again, the physics is actually nonlinear, and so you can't capture it fully as our system does by completely linearizing. And this is completely analogous to what we do, except we do it also with all the other things you need in order to get the power grid dependencies right. So instead of just looking at v squared, v4, we also do this with this complex power, which is, again, also U1 invariant, and so this makes sense. I hope that answers and clarifies this point. Very important point. I hope this is now clear. And then 2 more questions. How have you determined the stability condition that you mentioned in your slide? How robust is this condition? So the stability condition we determine is derived by this phase condition, and the detailed calculation is long and complicated, and I can't really give it to you here. How robust is it? This is a very good question. The condition we give ourselves, the condition itself, is actually robust in the technical sense of control theory. So if you have a perturbation of your nodal dynamics that has finite H and infinity norm, then we can tell you, like, we not always, but in at least some cases, we can tell you what the H infinity norm perturbation is allowed while maintaining this stability. However, we have to make some structural assumptions on the nodal dynamics. They're not severe. They're okay. There's, like, in the title of the paper, you will find the term voltage droop. And this structural assumption will not, our analytic result is not robust to perturbations away from this, unfortunately. This is a major pain point right now, and but it's something that we could not fix so far. Again, it's from an engineering point of view, it's a natural assumption to make anyway, so we didn't sort of kill the result, but we would really like to remove this to make it a properly in the technical sense, robust condition. It's not so far, unfortunately. Yeah. And slide number 13, what is the meaning of the state of the coupling? Well, it's maybe this is a bit of a fancy way to say it, but I'm just thinking the coupling between different oscillators. Well, what are the relevant variables? They're the voltages at the terminals and the current on the line. And what we care about is the amount of power that flows in the line and the amount of power that's actually contained in the line. And that is captured by the power flows, by P and Q. And also, another way to say it is, if you keep the voltage around, but you want to get rid of the current, you can replace the current by the complex power, and you have made a coordinate transformation of your coupling state. When the start coupling is usually sort of the current that is currently flowing, you can replace the current that is currently flowing by the power that is currently flowing. And now you have characterized it using invariant U1 invariant quantities, which I is not. The current is not a U1 invariant quantity. So that's all I meant to say here. Like, state of the coupling is not a technical term here. It's just sort of a motivation or a way to say, to connect to sort of the phase reduction terminology. I hope that is a little bit clearer. In a technical sense, all I'm saying here is I can switch from I to S as a coordinate, and then I get invariant or covariant equations here.
Okay, great. I think that brings us to the end of the questions. Thank you, Frank, very much. It was a wonderful talk and lots of interest. And thank you
for
very
the
much.
invitation.
And we are delighted to inform you that our upcoming webinar will feature Professor Dibakar Ghosh from the Department of Physics and Applied Mathematics of Indian Statistical Institute, Kolkata. It will be on October 27th, and the talk is on coexisting dynamics of swarming and synchrony in complex systems. So please mark your calendars, and we look forward to seeing you on October 27th. Thank you all and have a wonderful day wherever you are in the world. Thank you. Bye-bye.
Bye.
Bye. Bye.